Ground improvement techniques. In this subject, there are 5 units. In the first unit, there are 2 chapters, Introduction and Mechanical Modification. Unit 2, Hydraulic Modification. Unit 3, Physical and Chemical Modification. Unit 4, Modification by Inclusion and Confinement. Unit 5, In situ ground reinforcement. Unit 1, first chapter is Introduction to Ground Improvement Techniques. Ground improvement is the process of improving the geotechnical properties of soil, as the soil at the construction site may not be having sufficient strength to support the structure. As we know, the structure of a building is divided into 2 components, superstructure and substructure. The superstructure is the part of the structure which is above the ground level and receives the live load. The substructure is the supporting structure which transmits the loads of the superstructure to the ground. The purpose of the foundation is to distribute the load over a large area so as to bring the intensity of load within the safe bearing capacity of soil. Then what are the general requirements of a foundation? It must be sufficiently deep to be free from seasonal climatic effects. It must be placed below the organic or loosely deposited soil, if any. It must be stable with respect to shear failure and must not settle beyond a tolerable limit. The factors affecting bearing capacity and settlement of soil are type of soil, location of groundwater table, loads and type of foundation. If the soil is loosely deposited, it will be subjected to either shear failure or excessive settlement. To avoid this, it has to be compacted to the required density using the suitable compaction method. If the top layer is having organic matter which is weak in strength, or if the soil is contaminated, proper care should be taken to avoid failures. Nowadays, with the increasing population growth, urbanization and modern agricultural practices, the amount of waste is increasing and polluting the air, water and soil. The soil contamination further causes ground and surface water contamination. Not only the water contamination, it leaves many lands as wastelands. Even the acid rain, spillage of petroleum and chemicals also cause soil contamination. Hence, there is a need for ground improvement to enable cost-effective foundations and to reduce the detrimental effects of contaminated soil. Not only the contaminated soil, other problematic soils like expansive soils, collapsible soils, landfill soils also need ground improvement techniques before planning a structure above them. Now let us discuss the need of ground improvement techniques in detail based on the soil conditions at the site which demands the ground improvement. First point is low density and bearing capacity of soil at the site. If the soil is loosely deposited sand or under consolidated clay, the density of the soil will be less. As the bearing capacity of the soil depends on density of soil, even the bearing capacity will be less for low density soils. Foundations constructed on this kind of soils will be subjected to either bearing capacity failure or settlement failure. Another problem is swelling and shrinkage of soil. Swelling and shrinkage happens in most of the clay soils which are known as expansive soils. Based on the clay minerals presented in the clays are of 3 types: kylenetic clay, illite and smectite clays. Example for kylenetic clay is China clay, example for illite clay is red soil, and example for smectite clay is black cotton soil. These smectite clays swell excessively during rainy season and shrinks on drying. This exerts uplift pressure on the buildings. If the structure is lightweight structure, it will get uplifted and causes failure. If it is a heavy structure, then also it causes cracks in the walls. If it is a subgrade soil, even the pavements get cracked. The underground piping system also gets damaged due to these swelling pressures. Next point is problematic soils like collapsible soils, soft soils, organic soils and peaty soils. So these collapsible soils are unsaturated, loosely deposited soils with high void ratio. If they are subjected to saturation, they undergo a large volume change which causes excessive settlement and failure of substructures. Example is wind deposited soils. Then soft soils, they are having a large fraction of fines with high moisture content. This causes settlement failure. And organic soils are formed due to the decay of organic matter, which are initially fibrous in nature and later become as peat and muck. These soils are not suitable for construction because of their low shear strength. Then loosely deposited sands and gravels. The coarse grained soils, if they are loosely deposited, they may form sinkholes in rainy season and disrupt the foundations. Next point is foundations on dumps and sanitary landfills. In developing countries like India, there are many waste disposal sites where the wastes are deposited before the regulations are formed and implemented. These waste disposal sites are called open dumps. Here the pollutants are free to move in any direction and cause serious health hazards on living beings. The reasons for pollution are industrial development, population growth and modern agricultural practices. The pollution is caused by the release of organic and inorganic pollutants from various industries like chemical industries, plastic industries, mining industries, nuclear power plants, biomedical waste, radioactive waste, etc. Not only the industrial activities, the agricultural activities like the usage of chemical fertilizers and pesticides, construction activities, acid rain, accidental petroleum and chemical spills also release pollutants into the geo-environment. The organic pollutants will decay, but the heavy metals disposed to the soil will remain in ecosystem as they are not biodegradable and they are chemically hazardous as they find their way into human bodies through the food chain. The herbal products from the medicinal plants grown on polluted sites cause serious consequences on human health. The contamination of vegetables cannot be underestimated as are the major source of food for many living beings. The next point is handling dredged materials. Dredged materials like sediments near ports will be loosely deposited and they need to be stabilized or deposited in a safe place. Handling contaminated soils. The soils located at landfills, open dumps, mining areas and industries generally are contaminated. The commonly adopted method of waste disposal is by landfilling. If the landfills are not designed properly or if it is an open dump, the leachate generated in the waste will migrate through soil and contaminate the surrounding water sources. The foundations constructed on this kind of soils will be subjected to excessive settlement and there is a threat of methane gas explosion. Even the contaminants in the soil may react with the foundation materials and further worsen the stability of the structure. Next point is use of old mine pits. To reuse the old mine pits, for constructing the buildings. The pits have to be refilled with soil, but the refilled soil has to be properly compacted to avoid settlement problems at the site. Before refilling, the site has to be cleaned by using a proper soil remediation technique, because the soil at the mining site contains harmful chemicals which were used during mining operations. Next point is failure of slopes, effects of liquefaction. To prevent the failure of slopes, the slopes have to be protected with proper reinforcement or other techniques to improve the stability. The stabilized soil is less susceptible to liquefaction. Therefore, proper ground improvement techniques need to be studied to avoid the detrimental effects of slope failures and liquefaction. And the last point is reclamation of unusable land. To reuse the wastelands like open dumps, polluted lands, or lands subjected to soil erosion, proper ground improvement techniques are required to improve the engineering properties of the soil. Next topic is ground improvement strategies. So there are various strategies like avoid the particular site, design the superstructures accordingly, then remove and replace unsuitable soils, improve the properties of geomaterials, enable cost effective foundation design, reduce the effects of contaminated soil, ensure sustainability in construction projects. Then principles of ground improvement. In that, first one is densification of the ground. For portionless soils like gravel and sand, strength will be increased by compaction itself. Hence, densification of the ground plays a major role in the ground improvement of granular soils. Then second principle is accelerate the consolidation. In case of coarser soils like clays, the density will be increased when the pore water is extracted from the soil, which is a time-taking process. For such kind of soils, the consolidation process has to be accelerated by using some artificial means. Next one is usage of geosynthetics. For protecting the slopes from erosion or failure, they can be reinforced with geosynthetics. To provide separation between distinct soils or to isolate some soil, the geosynthetics can be used. Next point is usage of admixtures. For contaminated sites where improving the strength is not the main criteria, the pollutants can be removed or immobilized by using proper admixtures. This in turn protects the human health and environment. Next principle is preloading. The purpose of preloading is to minimize the post-construction settlement. Before starting the construction, the weak soils at the site are improved by applying some static load for a long duration. Next principle is mechanical stabilization. It is the process of improving the soil properties by changing only its physical properties without causing any mineralogical changes. It includes compaction and fibrous and other non-biodegradable reinforcement like grout to improve the strength. The various ground improvement techniques are broadly classified into three types: ground reinforcement, ground improvement, and ground treatment. There are various techniques like stone columns, soil nails, micropiles, then electroosmosis, blasting, then using some additives like lime, fly ash, dewatering techniques, vitrification, etc. Then what are the objectives of ground improvement techniques? The objectives may be one or more depending on the structural requirements. It may be to improve the bearing capacity of soil, or to reduce foundation settlement, or to enable construction on granular fills, or to provide temporary underpinning, or to provide excavation support, or to reduce foundation dimensions, or to construct shallow foundations, or to enable dry working conditions for foundation excavations. Then classification of ground modification techniques. The ground improvement techniques are classified as 5 types: mechanical modification, hydraulic modification, physical and chemical modification, modification by inclusion and confinement, then combination of these methods. So what is mechanical modification? This will be done by mechanical means like rollers or deep compaction techniques. The soil density is increased by the application of dynamic loads using various types of rollers depending on the soil and site conditions. Next one is hydraulic modification. This is the method of providing drainage path in the site and extraction of pore water from the soil, which improves the strength of soil. In coarse grained soil, this can be achieved by lowering the water table, but in fine grained soil, because it needs long-term application of loads to dissipate the pore water, preloading technique or stone columns can be used. So what are these stone columns? The stone columns are nothing but boreholes which are filled with aggregate. The stone columns are useful to densify the fine grained soils where compaction is not effective. These stone columns not only provide drainage path but also provide lateral support like reinforcement and improve the strength of fine grained soils. So these stone columns can be used for stabilizing soft clays of thickness more than 5 meter. The size of aggregate used for stone columns is 20 to 75 millimeter. Length or depth of stone columns is 15 to 20 meter and diameter is around 0.6 to 1 meter. The aggregate is placed inside the borehole and it is compacted by vibrating probe or ramming. The uses of stone columns are to increase the shear strength and decrease the settlement of soil. The next one is physical and chemical modification. Physical modification means changing only the gradation characteristics of soil, either by using inert additives or by thermal modification, whereas the chemical modification involves changing the mineralogical properties of the soil by mixing the soil with chemical admixtures. Thermal stabilization. It has been observed that heating or cooling shows certain marked changes in the soil properties. These heating and freezing techniques have been extensively used as soil improvement techniques, and these methods require electricity. Heating will remove the pore water by evaporation and densifies the soil. The temperatures can range from 300 to 1000 degrees Celsius depending on the type of soil. Proper care should be taken to avoid the negative impacts on adjacent structures. If high temperatures are used, this method even immobilizes the pollutants in the contaminated soil. In freezing technique, the pore water is converted into ice. The ice binds the soil particles and increases the strength. This method is used for temporary purpose during the construction stage, especially to prevent the walls of excavation from collapse. Then another method is modification by inclusion and confinement. The geotechnical properties of the soil can be improved by providing reinforcement to the soil. This reinforcement may be in the form of geosynthetics, fibers, strips, bars, meshes, or soil nails. So, in some situations where time is a constraint, it is better to combine either mechanical and chemical or mechanical and inclusion, etc. Next topic is suitability, feasibility and desirability. There are various factors which influence the selection of ground improvement technique for a particular site. First one is type and degree of improvement required. Before we select the ground improvement technique, first we should understand the problem at the site, whether the problem is with low bearing capacity or excessive settlement or slope stability or permeability or liquefaction or erosion, etc. After analyzing the problem, we should plan for the degree of improvement required for the proposed construction. Every time we need not aim for the maximum strength, but it should be sufficient to take care of the structural loads estimated at the site. The next point is type of soil, geological structure, seepage conditions. If it is coarse-grained soil, then mechanical modification is sufficient to increase the density. If it is fine-grained soil, then hydraulic modification is required to accelerate the consolidation. If it is contaminated soil, chemical modification is required. So, depending on the soil type, we have to choose the suitable modification technique. The geological conditions like location of water table, different terrains at the site also influences the selection. The seepage is a biggest problem for earthen embankments, hence proper seepage analysis has to be done for preventing the seepage loss or failure. Next point is quantity of work, cost and construction time. The ground improvement technique depends on how big is the project, what is the cost of construction, time of construction and also the quality of construction. If the project is big, the soil needs more strength over wider area, which will be achieved by proper selection of the technique. The next point is availability of equipment and materials. Some ground improvement techniques require sophisticated equipment and also skilled labor, and some materials are not available everywhere. Hence, these things should be assessed before selecting the ground improvement technique. Next point is possible damage to adjacent structures or pollution to groundwater resources. While operating the compaction equipment at the site, care should be taken to avoid damage to the adjacent foundations or structures. In case of chemical stabilization, even the chemicals should be carefully chosen to avoid pollution to the surrounding water resources. Next point is durability of the materials involved. Before selecting the chemical agents or grouting materials or geosynthetics for the ground improvement, the durability of these materials have to be assessed with respect to their long-term efficiency. If the chemicals selected are not durable, they may leach out from the site during the rainy season. Next point is toxicity or corrosivity of any chemical additives. The chemical agents selected for stabilization should not be toxic, should not react with the construction material, or should not corrode the foundation systems. Even the government regulations may restrict the use of few chemicals. The next point is reversibility or irreversibility of the process. Sometimes the chemical additives may react with other chemicals in the site which are already present there and form new compounds, which may worsen the situation if the compounds formed cause swelling of the soil. The next point is reliability of methods of testing, analysis and design. The laboratory testing processes to identify the properties of materials should be reliable, as they may misguide the entire process of stabilization, including analysis, design and field application. Next point is feasibility of construction control and performance measurements. Before starting the ground improvement process at the site, the quality control and performance related documents have to be prepared for better monitoring and controlling the ground improvement process in the field. The feasibility of a particular method is strongly related to the type of problem in hand: a foundation, an embankment, unsoft ground, an unstable slope, an excavation, an earth returning structure, a leaking dam or reservoir. Then the traditional objectives and emerging trends in the ground improvement techniques are to improve the bearing capacity or to reduce the distortion and stress, to reduce the compressibility or settlement, to control shrinkage and swelling, to control permeability, to reduce water pressure and seepage, to prevent detrimental effects due to environmental conditions, to reduce susceptibility to liquefaction, to reduce natural variability of porous materials or foundation soils, and to provide excavation support.